All right, welcome back. Where were we yesterday? Here. So this was about an application of geometric singular perturbation theory, which is quite important. And I'm trying to see where I should go back, what point. Yeah, this was, I think the whole story started last week, whereby I was talking about this simplest model for finite size particle motion. And I'm trying, yeah, this is really it, right? And this is for heavy particles, and it's meant to, and it's a steady model, and it's meant to explain the focusing phenomenon that one observes behind bluff bodies, like here somewhere in the middle. And I've been talking about that extensively, and in the end, it came down to us computing the reduced dynamics on the slow manifold, which I didn't compute explicitly, because I never wrote out the velocity field explicitly that was used in the paper that I was referencing. But I'm showing at least the velocity field itself, which has all these von Karman vortices, right? So this is the fluid velocity field, but at leading order, the fluid velocity field appears on the reduced order model on the slow manifold, right? But this by itself doesn't explain focusing, so we definitely needed the next term. The next term is luckily not divergence free. And I just showed you that in the paper, I believe numerically it was established that these periodic orbits here, most of them are destroyed, except for one that survives, and that acts as an attractor for the surviving fixed points. And then that explains why small particles focus. The big picture is that this is what happens in the slow manifold in the phase space. We understood the reduced dynamics, which is this red curve, and everybody else is just approaching exponentially fast and synchronizing with this limit cycle. A slightly more accurate model, still there are lots of terms that I'm ignoring here, but there's one more term added here, which would normally have some other coefficient, but when the particle was not neutrally buoyant, but for neutrally buoyant particles, it has the same epsilon coefficient that the acceleration has. Other than that, you have the Stokes drag still here. So the epsilon comes over this being 1 over epsilon relative to the others. And so the epsilon goes to the other side. And originally, this is 1 over Stokes number there. There are various non-dimensionalizations. And this model, or at least this treatment, even the previous model too, the general Maxey-Riley does allow for an unsteady velocity field, except that the prior treatments of that problem from singular perturbation theory, from a singular perturbation theory perspective, did not allow for those because somehow Fenichell's original recipe was followed always. But one can actually allow for time dependence, and I was showing you how one can account for that. So one then will restrict to a finite time interval at a time, so that whatever results we get, they will be uniform small enough epsilon type results for finite time intervals. And this is what the fast time is. So you now have a new slow variable, which is time itself. So we still have a slow fast partition, but the slow variables are now a larger set because you also include time itself. Okay, other than that, the calculation was similar. But also it led to the result that the addition of that material derivative with respect to the velocity actually killed all terms that would have introduced dissipated behavior. So this formal calculation shows that up to any order, all the phi i's are 0. So in fact, the reduced dynamics is equal to the fluid dynamics. And I told you that on the one hand, that's helpful because it's promising. Again, the statement is that small enough neutrally buoyant particles will follow the fluid particle motion. Therefore, when you do particle image velocimetry, which is all about tracking these particles, right, and having a picture of them, and then the piece of software would process those trajectories that the camera records those. The piece of software then works out what the individual between 2 pixels, which trajectory moved where, and you can use that to get velocities at pretty high resolution. And the belief is that those velocities are actually representative of the fluid velocities, which turns out to be true after some initial synchronization period, according to this model, right? However, when you look at the literature, that's not what people always find. And when epsilon is not so tiny, then they actually see pretty significant deviations from the fluid trajectories. So I started discussing that. Are there any questions so far? This is where I was, and basically I gave up the assumption that epsilon is tiny. So I scaled back to this mu, which would be the original Maxi-Reilly equation. I just rewrote the equation here, and I pointed out that this is the fluid's material derivative, which is the derivative taken along fluid trajectories. That's the notation. But in the physics literature, people had this great idea, which turns out to be very beneficial, to turn that into a material derivative with respect to the particle trajectories that we're currently looking at, because maybe we can exploit that. And that turns out to be the case. So if instead of this, I write the material derivative with respect of the velocity with respect to, not with respect to fluid trajectories, but with respect to finite size particle trajectories, which I've written out here, okay? Then in order for me not to change the equation, what I have added here, I also have to add to the other side, and also what I have ignored here, I have to add to the other side. So doing that, we actually came to the point that, that v minus u started appearing all over. So why not introduce a new variable, z, which is basically the deviation of the particle velocity from the fluid velocity. So it does have a good physical meaning. That's the type of quantity you're interested in. And in terms of that variable z, you get a dynamical system, which I probably accidentally said that it's linear. It's not quite linear, because Cu has a general nonlinear dependence on x, and x is a variable. But what I should have said with respect to the, once you know, say, let's just say this, once you know the particle trajectory x for the finite size particle, you could plug that in here. And then at that point, once you have the knowledge, then not that you could gain that knowledge without knowing z, because you have to solve this equation, and to solve this equation, you would have to have z at your disposal. So this is basically a wishful thinking. But once somebody gives you x of t, okay, then you can plug it in here, and then you just have a time-dependent coefficient matrix multiplying z. So formally, the system is linear in z, but in actual fact, this is a nonlinear system. Okay, it's just the dependence. Let's just say the right-hand side depends linearly on z. That's an accurate statement. In fact, true for both equations, but it doesn't make the system linear, because the main coefficient matrix depends on x. So this is where I was, and I wanted to see, and I'm in search of this phenomenon, which I think I've written out, which is scattering. So where's that coming from? So scattering, whatever it is, it's once again, it's a departure, periodic departure, or not necessarily exactly periodic, but say intermittent departure from the fluid particle motion. So it seems like that neutrally buoyant particles synchronize, and they do that for a while, everybody's happy, and then at some point something happens, something goes wrong, and the finite size particles desynchronize. And that might go on for a while, and then they synchronize again and desynchronize. And that's the scattering phenomenon that is unclear at this point where that's coming from. We know from geometric singular perturbation theory that it just cannot happen for small epsilon, because we had a general conclusion that tells us that the fluid particles are attracting the finite size particles. So somehow it's a finite epsilon effect. Okay, so here's how you can just deal with this. And I do this for two reasons. I think it's inside for physically, but also whenever I see a technical step or little tool that I can communicate without doing too much detail in a proof, then I will give it to you, because I think it's just helpful to be aware of. It's helpful too. So one estimate that people can do on equations like this is to reveal something about the magnitude of z is the following. So multiply, I should use bar. Both sides of the first equation here by z itself. So z is a vector. So I take an inner product. And the classic way, this is a trick that people do when they want to do energy estimates, and it works here as well, because what you get when you take the inner product, once again, these are either two or three dimensional variables, so the arguments are also working in 3 dimensions. What I'm going to do that works in any dimension, but the Maxi-Reilly equation is either 2 or 3 dimensional. So you have z times z dot, which is a classic trick to rewrite that as 1/2 d by dt. So there was a dot between z norm squared, right? And that's the case because z norm squared is just the inner product of z by itself, right? So when you hit that with time derivation, differentiation, then you will have z dot z plus z dot, but by the symmetry of the inner product, that's the same. So you have 2 times z dot. So you get the z dot back if you multiply it by 1/2. Right? So that's on the right hand side, on the left hand side, sorry. And on the right hand side, we basically have a linear function of z. So this will give me then a quadratic function. So I will have a coefficient matrix grad u plus mu I being the identity that multiplies z, and then I have z as well. So I have an inner product there. Now we did this when we did estimates for linear systems. I actually did the same estimate for linear systems in part 1 of this course. But it's not so much that the system had to be linear, but rather dependence of the variable of interest in the right-hand side had to be linear. So once again, this is not a linear system, but the variable of interest whose evolution I'd like to estimate has a linear dependence on the system, and that's what makes this estimate work. It's the same estimate I did before, because I think part 1 of this course, and it just simply says that when you have a quadratic form, then you can upper estimate that quadratic form by taking the largest eigenvalue of the symmetric part of the coefficient matrix, because remember, when you have a quadratic form, coefficient matrix can be general, but only its symmetric part matters, and multiply that by z norm squared. So first, so I will write that this is less than equal to the lambda max of minus grad u plus mu I, except that I already replace that matrix with its symmetric part. Now the symmetric part of mu times I is just mu times I, because I is symmetric, but the symmetric part of the velocity gradient is something we used before. The symmetric part of the velocity gradient is the rate of strain tensor. So I just write it out for reference. But that's true for any quadratic form that only a symmetric part of the coefficient matrix matters. So then I put S there. S depends on, continues to depend on x and t, as mu does. It's the lambda max and z norm squared. Okay, so on the one hand, so this is a differential inequality, which one can integrate by dividing both sides by z norm squared. Right? I'll just do that formally because it's been a while that we did something like this. So this is d by dt z norm squared divided by z norm squared less than equal to lambda max minus, and I write this out a little bit in more detail, xt plus mu I, and that's it. Now both are functions of time. So now imagine that you have plugged in the solution z of t that appears here and x of t, which appears here. You have 2 functions, one of them is strictly less than the other. Therefore, if you integrate both sides, then the integral by the additivity of the integral of the left-hand side will be strictly less than the integral of the right-hand side, right? So if you integrate in time, from say t naught to t, and I should probably be more precise, I'll just say dt tilde, right? then the integral on the left-hand side will just give me 1/2 times log, z of t divided by z t naught norm squared. This is the integral from t naught to t lambda max, blah, 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 dt tilde. So finally, what I should be getting is zt norm. I bring in the log. Is this correct? Log z. Yeah, okay. And less than or equal to zt naught norm times e to the lambda from t naught to t lambda max minus mu minus, what do I have here? S, and then I have to plug in here x of what? T tilde, okay? T tilde, S closed, mu I, and dt tilde. All right, let me move this a bit because things are getting a bit hectic there. So this is the lambda max of minus S x t tilde as the rate of strain tensor plus mu I. Okay, dt tilde. So we have a general estimate for zt norm. And the thing to observe is that this will give me decay, so it will give me a attracting manifold, no matter what, any initial condition, irrespective of the details, will decay to the manifold if, and I don't want to sweat the details, I don't want to just say if this integral is a negative number and goes to minus infinity, but I will just say, look at the integrand. And if this is uniformly negative, so I can bound it in norm, just not zero, but uniformly negative. So say I can replace it by minus epsilon separated from minus delta from zero. And when I start integrating that small, even just small negative number over infinite time intervals, and this will give me exponential decay. So therefore, then I have exponential attraction. And then once I do that argument, and once I think about that argument, I can say, you know what, I don't actually need to know the detailed dependence on t tilde. It's enough just to require this over the domain of x values in which my trajectory travels. And then I don't need to know the time dependence exactly. I just need to require that this eigenvalue, when I compute it in a relevant part of the domain, relevant part of the domain or relevant part of the manifold, because only x appears here and the manifold is a graph over x, and that's negative, then it's enough for me to secure the attractivity of the sole manifold and critical manifold. So why is that? Because I'm skipping here one detail which I didn't write out, but I said in words, is that z equals 0 is just the critical manifold, and that's just equal to m epsilon, if you will, once you have the epsilon parametrization. And this is for any epsilon, not just small. Right? Because if you plug z equals 0 in here, then z dot will remain 0 forever. So that is an invariant manifold. And on that invariant manifold, x dot is just uxt. So you immediately get the reduced order dynamics. You get the same result from this non-infinitesimally small analysis for epsilon that I got for the infinitesimally small analysis. So that also means that the reduced dynamics on the critical manifold, which is the same as the slow manifold and doesn't even have to be infinitesimally small anymore. It's just x dot equals uxt. And that's what I was getting up to any order in the small epsilon analysis, but now I'm getting it for all orders. So what am I doing when I'm analyzing the history of Z? When I'm analyzing the time dependence of Z, I'm trying to understand how general trajectories relate to that flat manifold. So in these coordinates, it's completely flat. Like so. And you have the actual fluid dynamics going on here. For neutrally buoyant particles. And then the other particles are coming in. And I'd like to see that they converge to fluid particles. Now, that is a question. I'm out of the realm of small epsilon in which that is assured by the fact that the critical manifold, I did the analysis, was stable. So this was just a reminder why this is important, that for me to get an estimate for the behavior of ZT. And what I got is that if over a domain, say U of the physical space, it's either R2 or R3, whichever I'm working in here, either 2 or 3 dimensional motion, right? If I find that lambda max of minus sxt plus mu I is less than 0, right? Then what the conclusion is that as long as I'm in that physical domain, so this number is negative, then I do have attraction to the manifold. So the physical, so as long as I'm in some domains, this is a graph over the x variables, right? So here I have, say, x1, and here I have x2. And in this picture, this is z. So as long as I'm saying in some physical domain U, in which this holds, and this really just depends on where I am in the domain and time. This domain may change in time, and will, because S depends on T here. Although my writing doesn't necessarily bring that out, right? So T is here. Okay. So that's a good thing, because that gives me an a priori estimate for parts of the critical / slow manifold that are guaranteed to be attracting, right? So then I translate this over. This is the same as lambda min of sxt plus mu I has to be bigger than 0. And that's a criterion for de facto for the stability of the slow manifold. So as long as my trajectory is in this spatial region, that the trajectory means the finite size trajectory, it will be synchronizing with the fluid motion exponentially fast. Now, this is no surprise to me, because for small epsilon, this was always the case. I didn't even have to check this, right? Now, do I see why I didn't have to check that from this? Because this should then apply to small epsilon as well. Yes, I see that. Remember, mu was 1 over epsilon. So when epsilon is small, then this tensor here is huge. And everything, all the analysis I've been doing is on a finite domain. So all the velocity field is continuous, bounded, and everything. So when I make this really large, then it really will not matter what the rate of strain tensor is, right? The eigenvalue, when I look at the maximal minimal eigenvalue of this matrix, will be determined by the maximal minimal eigenvalue of that huge number times the identity. And the identity and that huge positive number times the identity only has positive eigenvalues. So even the minimum is larger than 0, right? So it checks out. So this covers the singular perturbation limit that we have already analyzed. So then it no restriction in that case. On U in this limit. But you also see what starts happening when you move away from that limit. It's not at all clear at all. These are competing with.
Sorry. Yeah, sorry to interrupt. How did lambda min come into play if we had lambda max over there?
Because I changed the sign, yeah. Right, so I changed the criterion. There was a minus here, that's a good point. And that was a less than 0, and I flipped. Okay, so when you work through this, then it's the same as having for these tensors, it's requiring the lambda mean of the negative tensor to be larger than 0. Okay, that's a good question. Thank you, because I forgot to say that.
And this is, sorry, and this is motivated only because this way it is easy to show that for very, very small epsilons, it will always hold, or is there another motivation for this?
For what?
For switching to lambda min.
No, it's just that it's nicer to, I don't have to carry a negative sign. But
yeah. Okay.
Yeah, okay.
Right.
There was no, it's just more elegant not having to write 2 parentheses, right? Okay. Where was I? So there will be then a competition between the two. And it will be a meaningful competition because, you know, if S was positive definite, the eigenvalues of this matrix, so this is actually equal to the minimum over I of the individual eigenvalues, and I can read off the individual eigenvalues. The individual eigenvalues are mu, which are coming from here, okay? And plus Si. Before you say that the eigenvalues of a sum of a matrix are not the sum of the eigenvalues, and you would be absolutely right. I say that when one of them is the identity, that game is different, right? So that just modifies the eigenvalues. So when you add the identities or something, then this is true. So the mu comes from here, okay, and the eigenvalues come from this symmetric matrix Si, and see the Si is incompressible. The flow is incompressible. That means that the trace of the velocity gradient is 0. So the trace of the velocity gradient is the same as the trace of the rate of strain because of this relationship here. Okay. Because the trace of S is just the trace of this plus the trace of that divided by 2. So the two have the same trace. And it's 0. So that means that generally, unless all entries in the diagonal of S are 0, you will have positive numbers, you have negative numbers, right? And if the negative number here is very negative, then this minimum, I'm sorry, I'm pointing at the wrong thing, and this minimum turns into a negative number, right? So for very large strains, so very strain-dominated regions, this actually is meaningful from the physics point of view. When the fluid trajectory has to travel in a region where things are really getting tight, short turns and the like, so the strain is high strain regions, then this number, this tensor will have, you know, a large positive and large negative eigenvalues, and the negative one will be then a match for this mu, which is no longer infinitely large, and it can turn this over into a negative number, and this estimate fails. Okay. Now, when the estimate fails, of course, this was sort of a worst case. What happens when the estimate fails? Does that guarantee instability? No, because when the estimate, so to speak, fails, then this turns into a positive number. And then I just get that, well, ZT, you know, might grow or might decay. And if it grows, then it will not grow faster than that number. So I pointed this, I think, when we're talking about linear systems, that it's only sharp in one direction. So just because this turns to a negative number, it doesn't mean that all of a sudden I have instability. It just means that I can no longer guarantee the attraction, right? But at least what this shows is that that the estimate. So this is so this is a criterion for exponential attraction, 2 m naught equals m epsilon, as long as x of t, the finite time particle, is in U. Okay, but I also then see from here that for regions with high strain, criterion will fail. And this is a bit sloppy, but you see how high it's actually a competition between this mu parameter and SI. Okay, now that's the first thing that I can say, but that's not the only estimate. This estimate is geared towards giving upper bounds on growth, and it works when it's negative. It works anyway, but it's meaningful when that upper bound is negative. But there was the other one, which I also did for linear systems, that you can do a lower estimate. And that becomes interesting when you talk about instabilities, because then you can guarantee a lower bound, which if then grows, then you have instability. What's the machinery for that? It's the same thing. When you have this equality, which is still an equality, then you either do an upper estimate for the largest eigenvalue for what you have here, or you do a lower estimate for the smallest eigenvalue of the same tensor, right? So let me give a name to this. Let's call this, say, double star in blue. So then double star implies that ZT is larger than equal to Z of T naught norm. Okay. What am I doing? Where am I? I don't need the ZT naught, sorry. That was at an earlier stage. It's going to be where I think I'm, no, it's fine. Okay, then I know why I forgot to write. That's what confused me. So 1/2 d by dt z norm squared is less than or equal to, now I do a lower estimate, lambda min of the same matrix, which is mu. And I remember that it's only the symmetric part that matters. So I write only S. And this multiplies C squared. Okay. So sorry, it took me a while to converge on that. What bothers me is that I don't see the whole screen at the same time. It must be bothering you as well. My apologies for that. So this is what I concluded here at the bottom, and I concluded it from here. So instead of doing an upper estimate, I used the same principle. I took the symmetric part of the coefficient matrix and I took its lowest eigenvalue. So instead of lambda max, now I have lambda min. Okay, so I go through the same procedure that I use to integrate this inequality. Okay, I get nervous about when people just automatically integrate. No, it's not. It's not that. It's when they say, "Oh, it's a differential inequality or whatever." Let's just integrate both sides, right? But certainly you cannot do that when the variables are mixed, right? And so I don't know that I never follow that immediately how that works, and I think that's a dangerous path. But the argument to solving this inequality is what I have just described before. So you divide by Z norm squared, and then you view both of them as functions of time, and you have two time-dependent functions. One of them is always larger than the other at each point. Then the integral of both will have the same relationship because they're point-wise larger, right? And that's just the additivity of the integral. So what you get from this one, I try to write it in a way that it's again similar to this formula here, right? So what you get is that Z of T in norm is larger than equal to Z at T naught norm. And then you have the exponential integral from t naught to t. Now you have the lambda min of the same matrix minus s x tilde, x t tilde, and that minus multiplies both, plus mu I, right, dt tilde. And the argument is then the same. So these types of estimates, suppose this is a negative number, that's not helpful for my purposes, because if you estimate z of t with a decaying exponential from below, that doesn't prevent z of t from growing in norm. That's just an interesting observation, that it might be growing, it might be decaying. If it decays, it cannot decay as fast as this exponent, but it may grow or it may decay. But this becomes useful when that exponent is actually, or the integrand is uniformly positive. Because if this is uniformly positive, then no matter how you start the initial condition, this is always a growing integral, right? So that means that instability. So by the same argument, lambda min of minus s of xt over the whole domain plus mu I, okay? If that is larger than 0, okay, then I have exponential instability. Along this m naught equals m epsilon. And the equivalent criterion, again, I do the same. I switch the lambda min to lambda max. Again, no particular reason, I just don't want to carry all these parentheses. The final criterion is lambda max s xt plus mu I less than 0, okay? And that's a definite criterion for instability. So if my trajectory travels, my finite size particle travels in that region, then we have criterion for exponential repulsion from this m naught equals m epsilon, as long as x of t is in U. So what I mean is that this defines a region, and if your trajectory is in that region, or in terms of this picture, as long as your trajectory is traveling in the extent it's in the space of positions and velocities, so it travels, and when it enters this cylinder, right, then during that time, if the first criterion holds, then the trajectory will start going towards the manifold, okay? And if the second criterion holds, then when it enters that cylinder, the trajectory, whatever it did before, it doesn't really matter, because in this domain, it will start going away exponentially. But I can only guarantee that until I reach the boundary of that domain U. Okay? So that was interesting that we were able to calculate that explicitly. And needless to say, then we thought that this then explains the focusing that we see, right? Because for a general mu, if there are multiple regions like this, here and there, then your trajectory, which has been synchronizing with the manifold, enters one of these regions of instability and it'll go away. But then it leaves this domain, right? So then it will start coming back when it leaves the unstable domain. So then the geometry of the scattering would be this, that I now show, the whole slow manifold here. This is m naught, which is identically the same as m epsilon. And epsilon is no longer, let me just put it this way, that I can't say anymore that this is much less than 1, because this effect does need a finite epsilon. Okay, And what then happens is that if, when epsilon is very small, then this will be the predominant behavior. So when you start increasing epsilon, then what you expect is that this will still be the predominant behavior, but at some point, these regions of instability will start popping up here and there. Okay, maybe here. So these will be regions of instability. Outside of these, you will have stability. So these will be the regions of instability or repulsion. That's what we guess from this. And then when the trajectory comes in, generally, and it will have to come in normally because over the other region, you have the exponential attraction. So the trajectory start coming in and the actual finite size. So here you have the fluid motion on this one. Sorry. It's hard to write on this one, at least for me. So the fluid motion will know nothing about this. The fluid motion just does this. It's oblivious to this. It might note to itself that, hey, this was a high strain region, right? Did you feel that? It got really squeezed and stretched. But other than that, it's completely oblivious to that. But the incoming trajectories are coming, they're targeting some fluid motion. The vibration of the stable manifold in these regions still holds, but here now there's a change. So it comes in, and then when it enters these cylindrical regions, right, that I can erect here, then all of a sudden the instability kicks in. So, okay, I'm happily converging. It's whoops, now I'm in there. So I get pushed away exponentially, right? But hey, I'm now outside, and for a while, so I start coming down. So I start turning, right? But hey, it's instability again. And I start coming down. Instability again. Coming back to see what happens here. So what happens here is that my distance from the fluid trajectories is decreasing exponentially, but then the observer just sees that, oh, it's increasing again. And there's this intermittent behavior depending on the actual flow. So some flows may not have any of these, others will have a lot of them. Say in a turbulent flow, you might have a lot of these instabilities because in a turbulent flow, you will have these high strain regions, right? So we figured that's probably what happens. And then Themis did in this work a simulation, which I, again, using a model which I wanted to show, hopefully I find it. So this is that cylinder example. Now I found that not the best way of, but you might see this little thing moving there. So that's going to be my pointer that I just figured out this morning how I can point. This is the trackpad of this laptop so I have a keyboard attached to it and it has a trackpad. Okay, so what you see here is the slow manifold, or generally speaking, not so slow manifold, this invariant manifold in the y equals u of xt coordinates, right? So y equals u of xt, which is the fluid velocity defines an invariant manifold. This is not the z coordinate. What you will see is in the z coordinate is up here. Now, how do I move this? Oh, I was so happy that I found this way, but now it's not. Oh, okay, it's more like this. Okay, the laptop is, the keyboard is upside down, so I was moving to the left. It's like, okay. So see that? That's the flat z equals 0. That's a little other coordinate system in which the z equals 0 plane is the invariant manifold. And you see two things there. You see the cylinders, that's just symbolic, right? Because the cylinder doesn't have z velocity components, that's just to give you a sense of where the cylinder is. But you do see domains of instability that then is computed back then. This was, boy, it's a long time ago, maybe 11 years ago. And the walls that I was talking about, these vertical walls that are transparent. And now you see the 3D view of the same thing. See on the blue is basically the color map is such that when it's blue, then you have stability. And when it turns into red, then you have instability. And the boundary of that is this curve. There are several of these spots. And again, he erected a wall here. So if the incoming trajectories enter that wall, you should be seeing instability. Also, mind you, this is now an unsteady flow model. So this whole picture will be breathing. In the upper picture, you will not see a change in the manifold because it's always flat, but you will be seeing a change in the colors and the locations of those instabilities. But in the lower one, everything will be moving. The manifold, because it's a time-dependent manifold, the location of these, the number of these, and all that, a time-dependent flow. And what he computed is 3 different initial conditions that I forgot if all of them are off the manifold. One might be on the manifold. We'll see. I think all 3 are off, but some of them will be at least one of them will be traveling in a way that avoids these instabilities, and therefore it will be attracted to the manifold without any interruption. But he selected the other 2 in this cloud. The cloud is off the manifold, right? Such that they will enter these regions. And now let's see what happens. Yeah, the white one passes by and all the others are jumping up, but then they come back down once they're outside. And especially that's particularly apparent in the upper figure. But also see that these regions come and go, right? So new ones are born all the time. Let me run it again. And then maybe I can just go through like that. Yeah, see, so they started, if you look at the lower figure, all of them are converging to the manifold. But the one of them enters that region and immediately shoots up exponentially. And now the second one entered as well. They're going up exponentially, leaving the manifold. And you see that in the upper figure here, right? That there it's pretty apparent that the distance from the manifold goes. But then once they leave those dangerous regions, they are coming back down again. And the one down here, which never entered any of these regions, is just happily converging to the manifold. You might ask, why is it intersecting the manifold? It's not supposed to. That's just a time dependence, right? It never intersects the manifold right when it's there, but it has already passed a point and we're still showing the same trajectory, but the manifold is changing in time, right? And that's why it's the reason for that. So this was pretty fascinating and a nice general explanation for this focusing phenomenon. But that got us thinking that it's actually surprising that for general invariant manifolds, you can do such an explicit calculation, because in many ways, I mean, the Fenichel type or Lyapunov type numbers I showed you, they are idealized and they're very powerful. They arise in the proof of the existence of the manifold, but in practical calculations, you won't be able to calculate them, right? I mean, I gave you a sense with the homework problem for simple problems, but for anything like this, to calculate the Lyapunov type numbers is hopeless. You would have to know the exact asymptotic dynamics of the reduced system. However, this, without any knowledge of the dynamics, so these regions were calculated just in the simulations from this relationship. And you know the rate of strain tensor from your data or your model, you know your mu. So all you need to do is just linear algebra. And linear algebra gives you a prediction for these patches of instability on a nonlinear manifold. So we thought, well, maybe, you know, this sounds like a useful general tool that is actually way more computable than the Lyapunov type numbers and give you very specific predictions. Just to give you an idea, this may well be an asymptotically attracting invariant manifold. In fact, just imagine that the fluid here kind of settles downstream, and the no high strain regions, that ultimately everything is attracting to this manifold. And all the Lyapunov type numbers, because they're asymptotic in nature, would tell you that. They would tell you that this is a normally hyperbolic attracting invariant manifold, but they would be missing all this story. Or if there's a diversity of asymptotic behaviors, then what will the Lyapunov type numbers tell you? They will tell you, sorry, the theory of normally hyperbolic invariant manifolds doesn't apply because some of the Lyapunov type numbers are positives, the others are negatives. Some trajectories will go away, others are sorry, we can't help you. So this is a whole lot more practical and you can calculate it in any given problem, right? And describe your invariant manifold. So we just wrote out in a paper a general formulation, and that's what I wanted to give you, because to date, I think this remains the only sort of computable characterization of the stability of invariant manifolds. And once we did this for this problem, it wasn't hard to generalize it, but the idea really came from this problem. So more generally, you can, I think we call these transient instabilities or something like that. And maybe it's the opposite. Maybe it's the stability that's transient. So these can be identified along invariant manifolds. And especially when you have finite time data, this is really more important than the asymptotic Lyapunov type numbers, which you won't be able to compute because you just don't have enough data. So this was in a, where was this? I think yeah, this is, he then used it for actually more recently to describe random, not random, extreme events with another student of mine, Mohammad Farazman, who was a postdoc then now a professor. That this is the picture that they're still showing in their slides, is that basically an extreme event would happen in a dynamical system and you move along some sort of attractor, which is ultimately an attractor, but it has localized instabilities, bumps. And then their characterization, the very nice characterization that the dynamical system does something like waves in the ocean. Fundamentally, we picture that as a dynamical system within an attractor, and all of a sudden comes a rogue wave, which is huge, and then it disappears, and maybe it's there for a while. Why is that happening? And their way of characterizing is that there are these little spots where you have these intermittent instabilities to a manifold or an attractor, which is otherwise attracting, right? But if you happen to run into these, they might be small and rare, then all of a sudden you see something which is uncharacteristic, but it doesn't last long because you get out of that region. So that's really a beautiful piece of work they did for extreme events. So this paper was, I think, so it was the Science Journal of Applied Math. No, Science Journal of Applications of Dynamical Systems. I think 2010. Okay. So the setup is more general. So you have a dynamical system F, which is now autonomous, unlike in Fenichell's case. This is a n-dimensional dynamical system. Time dependency is general. I'm not assuming that it's time periodic. And you have a flow map associated with that maps initial conditions to current positions. So that's fairly general. And the only assumption is that we have a time-dependent invariant manifold in Rn, right? Which is new sort of relative to the Fenichell's setting. So what we assume is that this is a k-dimensional locally invariant manifold. So it means that you may have a boundary again, and as long as you don't reach the boundary, you're inside the manifold, you stay on it, but you may leave through the boundary. And what else did I want to say? So in a non-autonomous setting, what we mean by an invariant manifold is not that it doesn't move, it will move, but it's like a material surface in continuum mechanics. So if you apply the flow map to it, to its position at T0, okay, then it will be part of MT. Capital T later, right? So this is for all T less than or equal to T0. That's what it means to have a time-dependent invariant manifold. To kind of reconcile it with the picture that I've been drawing for manifolds, let's just look at things in the extended phase space. So I will have time here, and I will have, say, some of the variables, say x1 is here and x2 up to xn are here. And such a manifold in the extended phase space starts, so the dimensionality, it's k-dimensional, and you somewhere initialize it, say here at time equals, so this is t equals t naught, and then you have some initial position for that manifold here. So that would be m t naught, m of t naught, okay? And then you let it go, and it will be a bona fide invariant manifold that doesn't move in the extended phase space, but in the traditional phase space, which is just the x variables, it will be moving. So what do? You start individual trajectories from it. That's how you evolve it. And as a result of that, if I now take another cut at some, where's my color? At some other time, so I take a cut here, a constant, this is some sort of t cut, then it may have deformed into something else. Well, I just drew the same thing. So let me give you a feel for the deformation. So at this point, that cut might be something like that. Of course, I have to match up the trajectories, right? So these are, oh, sorry, it's too thick. These are the intersection points of individual trajectories. Okay, so they run. And then this would be m of t. So this whole manifold, and it has a boundary, generally speaking. So this whole manifold, as I'm showing it, would be an invariant manifold, a large invariant manifold, which is steady in the large extended phase space, but its time equals constant slices keep changing. So that's what you observe. Say if this was again a fluids problem, you would observe this as a deforming material surface. Okay, I just include that term there because that's used in fluids and continuum mechanics. So this is a material surface. Okay. Now it doesn't have to be time dependent. Maybe it's time independent, but and maybe this manifold is just autonomous. That's this equation is autonomous. That's fine. But we wanted to motivate it by these fluids applications that we've seen. We wanted to make it time dependent. If it's time independent, then there's no reason for you to go to the extended phase space. You would be just doing this analysis in this phase space in which it just doesn't move. Or if you still use the extended phase space, then it will be boring. It's just we'll be doing that. Okay, so and this is really easy to set up what we have been doing, basically the normal attraction, and well, it becomes computational and notational and everything, but the idea is pretty simple. So if I now draw, this will be, I think of this manifold now as something that you've seen in the movie. So I think of this as now something changing in time, okay? And that will bring in inconsistencies a bit because I'm only able to show one snapshot of it, right? But I need all the space here. I can't just work on this projection here. I need more this time size. So I need just one of these sheets, and this is deforming in time. So I just want to do a setup which is very similar to what Fenichel did. So I have a motion on that manifold, a trajectory. So that will be, it starts from a point P, and right now it has run into another point Q, and Q is just the application of the flow map from T naught to T. I didn't have that burden when I was sketching the Fenichel results. I only had one index here because that was an autonomous setting. This is a non-autonomous setting. So I have to carry always the initial time, and the manifold itself is moving. So this is the application of P. I'm interested in assessing things in the normal direction because I'm interested in the normal stability of the manifold. So given the dimensions of my figure, this will be without an arrow, this will be just the normal space at P to the manifold at time mt naught. So now I have to carry that because P, that point, which is right now on the manifold at T naught, will generally be not be on the manifold for other times. So I need to carry that T naught there. And I will be interested in the evolution of perturbations relative to this other normal space here, which is normal space at F, T, naught T, P. So that's my base point, Q. And to the manifold at M of T. So those are then different times, T and T naught. And this is the inconsistency of the figure that this is breathing, right? So you should interpret this part of the figure as happening at T naught and as if you were watching a movie, right? And as this progresses, the manifold also is deforming in this representation. Okay, so that's the inconsistency that I was referring to, but hopefully that's something you can process in your mind. So what I want is a perturbation again. So this will be, I think I called it W naught in the notes. And the W naught is in that normal space at time T naught. And I'll be using the linearized flow map, which I again have along that trajectory. This is, I didn't give a name to that trajectory, but this is X of T. So along that trajectory, I map that vector forward. And remember, that will be just a general vector here in the tangent space of Rn to itself at that point. But just as in the Fenichar case, I'm not so much interested in that vector, but I'm interested in its projection. So my ultimate objective is understand this vector here. But I need to say what the other vector was too, I just realized. And for that, do I have enough room here? So this is the df T naught T taken at P applied to W naught, right? Okay, and I'm projecting it down, and this is the main player in whom I'm interested. This will be a projection there, right? It's the same idea, a normal orthogonal projection from the tangent space of the whole ambient space there. So this is the element. Let me give myself more room there. This is the element of the tangent space, and I don't want to carry all the of Q at Q of Rn, the ambient space. Okay, and this projection is defined on all vectors that are locally sticking out. So imagine a little copy of Rn here, right? And this is based there, and it's specifically a projection onto the normal space there. So I don't want to have too much notation. That's why I'm skipping the introduction of various quantities, but hopefully you get the point. So this projection operator now depends on where I am. So it will be based on at F T naught T P. That's the base point of the normal space. But mind you, if I just say this, then I'm only saying where I am. And I can be, this just gives a point, Q. But that point may or may not be on the manifold in a general case. So, and this projection will, generally speaking, depend on time, because the manifold deforms, so its normal space deforms. So I have to add that T here, because there's a fundamental time dependence on the projection operator itself. It's not just where I'm projecting, but also how I'm projecting, because the normal space changes its orientation. And I then take that and apply that to this derivative map, which has carried forward W naught, and this is what I defined as WT. Okay, so that's WT. So once I have that, I'm unlike, you know, I don't have to do all the heavy lifting that Fenichel ought to do in his theorem, because I assume to begin with, that's why it's kind of a cheap theory, because I assume that I know that this invariant manifold exists. Okay, I don't have to do the work to prove that it exists. So once I know that for one reason or another it exists, okay, and you know, I can generate invariant manifolds like that. This is a fluid flow. I just put down a bunch of initial conditions and I start running those, and they will give me an invariant manifold like this. And then I can ask, is that invariant manifold relevant for other fluid trajectories, not necessarily fluid trajectories, but finite size particles? Will this be a noticeable entity? And the answer is yes, it will be if it's attracting all the others, and it has to be in a region where the criterion is satisfied, and it will be attracting all those finite size particles. But of course, that criterion keeps changing in time, so I would have to reevaluate that. But what I'm after is defining a normal measure of attraction or repulsion. So I think we called it normal infinitesimal the Lyapunov exponent. Because the Lyapunov exponent generally measures separation of trajectories, and this one is specifically measuring, well, infinitesimal refers to this one, that this will have to in the end be very small, infinitesimally small, and it's normal to the manifold. There are probably better names to this, but we wanted a nice acronym, so that gives NILE. And the way you define it, it will depend on the initial location, and it will depend on how far you've been traveling in time. Actually, as I think about it, it both depends on the initial time. Sorry, it will be instantaneous. All these, because in the end, I will take the limit of this going to that, because I want. Sorry, that's what I forgot. As I was looking at, wow, infinitesimal, all Lyapunov exponents are infinitesimal. Why did you say that back then? Well, we said infinitesimal because it will be infinitesimal in time. So we'll be taking this point and make it come back here. So when you take that limit, then you will be getting locations along the manifold at any point t0 in time that are just about growing right then. So that gives you a continuous time monitoring of the manifold and tells you what are the locations where things are growing right now and decaying right now. And that takes out this whole time interval question from the picture. So that's why infinitesimal. So this will be infinitesimal in time, because all the Lyapunov exponents are infinitesimal anyway in space. They are about the evolution of infinitesimal small quantities. So for that reason, this will be characteristic of a given time and of a given location in the manifold. And the way it's defined is the limit of the time. This is the time that has elapsed. So this will be, at this point, I will rewrite the difference between the two will be, where do I write that? T minus T0 will be S. Okay, but I will, since in the limit T will be equal to T0, I just make it relative to T. The two will be equal anyway. So I will not use T0 to label the time, but I will, because Y carry that extra index, but I will be using T. The two are the same in that limit anyway. So it will be 1 over S times the logarithm of what? Well, simply we went through this thing in the case of the Fenichel construct. And once I ask, I have a linear operator that takes me from this normal space to that normal space. And I want to see the ballpark growth, say the largest growth that I experience, or the smallest or the largest growth or smallest decay, fastest growth or fastest decay, then I will have to do this for all the vectors here. I'm only showing one direction, but this is a multidimensional normal space in general, right? So I will have to take this operator, this one, and apply it to all sorts of W naughts and ask for the largest rates that I get for stretching or contraction rates. So that's just the same. Since I'm doing for all inputs, that's the same as essentially evaluating the operator norm of this, because that gives you a magnification factor, right? So that's why it's enough then to pass to the norm of that operator. So this will be the classic operator norm, which once you represent this in a matrix, in a finite dimensional problem, you know how to calculate that. You just multiply the matrix by its transpose and take the square root of that. It's a matrix whose square root you can take. So the largest, find the largest, basically the largest singular value of A, but that's the procedure you would calculate that. A times A transpose, and you would look for the maximal eigenvalue, take the square root of that. So this, what's the operator? It takes a while to write it out. So this is pi, and it's starting from this point F. I'm starting from T now, right? That's my base point, and I run up to T plus S from this point P. This is the point that I reference spatially with this number, and S will be going to 0. And I have to take this projection at the end time, T plus S, and that's preceded by me applying the linearized flow map from T to T plus S at the point P. So think of this as something that is growing at a rate of e to the AT, this norm. That is actually e to the AS, because the running time, the T, is the base time, which is fixed at the beginning. So the time that's elapsing from that is S. So think of this as e to the AS. So when you take the log of that, that gives you AS. And when you divide by S, then you just get A. So that's the exponent that we're trying to get out of this, right? If this exponent is positive, then you have instantaneous growth. If this exponent is negative, you have instantaneous decay at this location at this time, right? Very importantly, there's no, so this is the 9. And there's no asymptotic limit in this. And that's what makes it computable, because at the end of the day, you're actually never even stepping forward really in time, because you're taking that S to 0, right? So that actually makes it computable. So this might seem intimidating, but especially when you have a good idea of what the manifold is, this is really just a linearized flow map that you're using, the deformation gradient, to compute that and take this limit. So if you so the meaning of this first is that when you have sigma less than 0, that means local attraction. When we say local, it means both local in space, right? And time near P, and at the time, right there, right now. And when sigma is bigger than 0, you have local repulsion. But the question then remains is how to compute, and I'll just give you the formula. It's in the paper. And the formula is particularly simple when you have a graph for the manifold, as we had in this problem. So assume that you have a splitting of two kinds of variables, and that mimics the setup of the fluids problem, but without mimicking the details of the fluids problem. In this case, it's easy. This is defined irrespective of the dynamics, defined along any invariant manifold. And numerically, this is not, you will go into it, you will basically, you will only be using the rate of strain tensor, and you just have to basically project, you have to do a projection of the rate of strain tensor in the end, it turns out. Why the rate of strain tensor? Because when you take that limit of the flow map, then the linearization will come in, and when you take this operator norm, then the rate of strain tensor comes in. And that will be apparent in when I write this out, actually for the case which motivated the whole study, where you have the splitting of variables, no epsilon anymore. This is not a slow, fast splitting, just general two dynamical systems. But the assumption is that MT is defined as a graph, y equals, and I think u phi of xt, right? So the assumption is that the invariant manifold in this coordinate system is something really simple. It's just a graph. You might know it analytically, or you might know it numerically. It's your x and y, and the invariant manifold is this m of t given by this particular function. Okay, and it's moving in time, and it can be very complicated, but one set of variables is enslaved to the other. You can always do this locally, by the way, along any invariant manifold. You just introduce local coordinates in which it's a graph. So then the way to compute this and see the paper we just need to, it's actually fairly simple. So sigma pt is just the maximal eigenvalue. It has the same type of structure of the symmetric part of now a general matrix, which we call gamma. So that mimics the role of the rate of strain tensor. But what's that gamma in this general setting? Okay, where this tensor gamma of xt can be calculated as follows. You take the g component of this dynamical system here and differentiate with respect to y and plug in the manifold that you know is time dependent. And from that, you need to subtract the x derivative of the function that defines the graph of the manifold, x of t, and that multiplies fy, x phi x of t. Of course, these have to have the right dimension. So this is a Jacobian, which is if x is n-dimensional, y is m-dimensional, then this is an m by m matrix because y is m-dimensional and g was that, okay? Now this is I'm differentiating this function which maps into Rm with respect to the x variable, which is n. So this is m by n, but then, sorry, it's switching display. But this also has the matching dimensions because this is the n by m. This maps into Rn given that it's x, and then this gives m. So ultimately, when you multiply these two, you also get an m by m matrix. So that's it. So these two formulas, which could be summarized in one, it's just that they would be very lengthy. They give you how to calculate it. If you want to just check it for the example that we had to see if it checks out. So in the example, we had, what was the example? Say it's a two-dimensional inertial particle motion. So x and z were the variables that were two-dimensional, and we had x dot equals z plus uxt. That was the equation for the displacement. And z dot equals minus grad u of xt plus mu y. This was the equation I was working on. And this is what motivated all this. So in this set of variables, if I want to apply this general theory, it's slight inconvenience that I will have to think of y will be playing the role of z. Okay, this is how in in this general setting, there was no reason to use Z in that paper. So I'm citing in that. But in here, for some reason, this set of papers was written in Z language. So we just have to make that correspondence between the two. Okay. So in this case, remember that M naught, which is the same as M epsilon is not even there anymore, was simply defined by this Z equals 0. So in terms of this picture, this was the manifold, right? So when Z was equal to Y. So it's a completely flat manifold in this set of coordinates, all right? So when you have that, then of course, everything becomes much simpler because this gamma xt matrix, which is the heart of this whole calculation, starts out fairly simple, given that since the manifold is flat completely, so phi is the graph of the manifold, okay? This term is 0 because this is the equation of the manifold. So this is to be compared with that. So phi is just identically 0. So that means that this term is out, which means that this whole second term is out, and all I need to worry about is gy. Now remember what y was. Y is just z. So I need to look at the second component of the equations and take its partial derivative with respect to z in the current context. So that will be just minus grad u xt plus mu I. Okay? So when I take the gamma transpose route, so I calculate sigma pt, and the quantity I need to evaluate is this. So I just follow the recipe here, minus s xt plus mu I. And this is S delta U plus delta U transpose divided by 2. So the same type of quantities come in the exact same way. So when you then evaluate these, then you will get the same result. And the movie I've already shown you once again with some new meaning. So this, you can think of this now as a completely general invariant manifold because we have the result for that. And you will have these localized instabilities, these patches from predicted from the general formula. And this is the type of behavior you will see. So even though the invariant manifold in general might be attracting, there could be these localized instabilities along the way. Okay. I'm done with this part. And what I'd like to do in the remaining lectures, well, depending on this semester is running a little bit different from the last one. So when you look at the notes, I didn't have to do much chaos in the last one, last reincarnation of this nonlinear dynamics 2, because in nonlinear dynamics 1, I covered most of it in that year, because when I work on the blackboard, I can go faster. But with this sort of tablet, it's slower. So this is slightly different. So I will not have as much material to cover as I did last year, but I'd like to cover some of what I discussed then. And what I felt was useful to see how these results come about existence of manifolds. At least give you sort of a little survey of how you prove the existence of invariant manifolds. What are the approaches, just general? Because again, some of these techniques are just useful in their own right. Maybe because to me, an invariant manifold is always so mysterious. Once I know that it's there, it's good. But how do I prove, say, if I know that there's a stable subspace, how do I prove that it has a nonlinear continuation? What are the tools? What are the considerations? Do I learn something from that? So I just want to give you some ideas how that goes. So there are three basic methods, and I will give you an example of one of them, but perhaps the most classical one is called, which I will give you an example of, although that's one of the more limited ones, but it's not as technical. It goes by the name of Lyapunov and Perron. And this is good when so the manifold is then constructed as a solution of an integral equation. Of a global integral equation to which you transform your ODE. We'll see how that works, but fundamentally, the idea is simple. You have an ODE is something dot equals that. Why don't you integrate both sides? Of course, this doesn't solve your problem because the right-hand side still depends on the unknown. If it's not that simple, that's why we have a theory of ODEs rather than just theory of integration, right? But formally, you can convert an ordinary differential equation to an integral equation, and that what might seem like a headache, but on integral equations, there's no differentiation anymore. There are integral signs, and there are very nice estimates in analysis for integrals equations, right? Or integral signs in general. And there are fixed point principles as well, which apply to these types of results. So you often, even the existence and uniqueness of solutions for ODEs is proved using integral equations. You show that the integral equation, which you can formally write down for an ordinary differential equation, has a unique solution under certain assumptions. And you show that, as we'll see, hopefully if I have time, by a contraction mapping principle. Now the same goes for manifolds, right? But you need to have good global coordinates because you need to be able to write this equation down globally. So there's not much I want to draw about that right now. I'll just give you an idea that somehow we're shooting for. It usually works when you know a fair bit about the system. For instance, you know it has an equilibrium point, and you're shooting to find a manifold, invariant manifold that goes through that. And generally speaking, the integral equations are helpful if you have good coordinates over a whole domain of interest. So here you need to have good coordinates, over which the manifold candidate is a graph. Because when you start out with a dynamical system, I always assumed we had good coordinates, right? I've written out the system. Where's my system? Yeah, they're given in coordinates. What's the big deal? The deal is that these techniques don't work when your system is so large that the manifold, might start folding back and doing funny things. And then you can easily have invariant manifolds like that. But you have to have a region in which you trust that's not the case. That's what I mean by good coordinates. And you might need to do an initial change of coordinates to achieve that, okay? But other than that, then when you have that, then in this case, the manifold is a solution of an integral equation. Well, I already said that, global integral equation. All right, I said that. So the second, which is the more powerful but also more technical approach, which Fenichel has employed, that also has actually a classical approach. But so the original idea, as he credits it, is Adamar's idea. But Fenichel uses this. And then that goes by the name of also the or graph transform method. So the graph transform method doesn't necessarily need very good global coordinates. It's enough, however, but it does need to have a set of coordinates over which the manifold is at least locally a graph. Because fundamentally it's a local construct. So this just needs local coordinates. Again, you always have coordinates in practice for your dynamical system, but your manifold candidate might not be a graph over them because it might be just all across the board, right? So when I say you need to know enough about the possible location of the manifold when you want to show its persistence and stability type, because that's what these results are all about, right? Under either addition of perturbations or addition of the nonlinearities. So this needs local coordinates only. And this construct, it again comes down to a fixed point problem. So constructs manifold as a fixed point of an abstract mapping, which is called a graph transform. And a graph transform is you're still looking at a finite neighborhood, so some finite set, but over that set, the graph transform, what it does is that you have some candidate for a manifold, which is usually not an invariant manifold. So this is just, let's call it just some graph that you draw using these local coordinates that you have, you don't have to have a global understanding of that in one coordinate, but maybe, or individual coordinates. My picture is misleading, right? Because everything is so nice that I could take this as a global, so, but generally speaking, you know, you can have a something like this, and then you have coordinates here and there, and that qualifies, as opposed to this one, which has to have the global coordinate here. I think I should probably revise this figure because this is still a graph. But anyway, in those coordinate systems, these are, so imagine that you had something like this, and then you have the local coordinates, and then you kind of piece them together, straighten out that, and this is the straighten out manifold. And in that setting, you have a trial graph, and you will need to have assumptions on the dynamics so that there will be fundamentally a strong push normal to the manifold. And that's why the idea of normal hyperbolicity is so important in Fanichel's work, because that will then give you, when you apply the flow map to it, then generally speaking, when it's overflowing, it will push you, say, downwards, because it's pushing from the direction, it kind of straightens you out a bit. So when you apply the flow map to the whole graph, you get something that flattens out a bit more, and it's not so bumpy anymore. So then there's an operation that you apply additionally, which then actually says, you know what, I'm going to cut off what's outside. So my picture wasn't correct in the sense that the original graph is only defined, or it's only taken within that domain of interest, which is not necessarily small, but it's compact. And when you apply the flow map to it, then you will have to have general estimates that it gets squeezed in this direction, but also you can't control some of it will get out. Now you cut those off. And the graph transform is just the application of the flow map to a graph. And then whatever is outside your domain of definition, you cut it off. That's the graph transform. Okay. And so basically you seek fixed point of this operation that so this is the cutoff that defines a mapping, and see if and you don't care about this overflow, you don't care. But if you arrive at a point after repeated operations of repeated applications of this, that at every point you get another graph which is flatter, then at some point you get one which is then not going anywhere, because after this repeated application you might be flowing out at each application, but since you cut it off, the invariant manifold will actually just be a fixed point of the graph transform. So this is the invariant manifold. All right, and there's a third one, but I have to stop now. Sorry, I'm in overtime already. And that's purely topological. That's not going to take much time to explain. So that gives you existence, but no smoothness. And then what I want to do is just walk you through quickly how this method applies in the simplest case to prove that there is a stable manifold. So you linearize at a point, you have a stable subspace of a saddle point. How can you actually prove that it will have a nonlinear continuation using the integral equation method? And that's probably the simplest setting, and I probably won't write everything out, but use my notes and I'll walk you through them, because some of the estimates and the techniques are really helpful, I think, from an applied math perspective. Any questions? If no questions, then see you next week.